Hello everybody. In this video, we're going to look at exponential functions. You've already been introduced to exponential functions in the exploration that we did in class. So we're going to start with the definition. And the definition says, let A and B be real number constants. An exponential function in terms of x is a function that can be written in the form f of x equals a times b to the x power, where a is non-zero, okay, b is positive, and b cannot equal 1. The constant a is the initial value of f, meaning the y-intercept, or again, to find the y-intercept, you're plugging in 0 for x. So b to the 0 is equal to 1, and then 1 times a is a. And b is the base. Okay, so in the first example, we're just going to practice identifying exponential functions. Okay, so in this table, which of the following are exponential functions? Well, the first one is f of x equals 2 to the x power. That is exponential. You can tell because the exponent is the variable, okay? So the initial value here, meaning a, is actually 1. So if you don't see a there, it's understood to be 1. And the base, or b, is 2. All right, the next one is g of x equals 4 times x to the negative 3 power. This is not exponential. This is actually a rational function. But for now, we'll just say not exponential. Okay, the next one is h of x, which is 5 times 2 to the negative x power. That one is exponential. Again, look at your exponent. It's a variable. Here, the initial value, or a, is 5, and the base is 2. Okay, and then our last one is k of x, which equals 2x minus 1. This is not exponential. This would actually be a linear function. But again, we'll just put not exponential. All right. Next example. The next thing you want to be able to do is evaluate exponential functions. Since you are plugging into the exponent, this is going to bring up some properties of exponents, okay? Here is an example. We want to find f of x when x is equal to 1/3. So, essentially, we're finding f of 1/3, which means we're just going to plug in 1/3 for x, which is the exponent. Now, this is a fractional exponent. So, remember that fractional exponents convert to roots. For instance, you might remember that if you have, I'm just going to say x raised to the m over n, that is equal to the nth root of x to the m power. Okay, so we're actually using this property, being able to convert between fractional exponents and roots. Okay, so this would become negative 5 times the cubed root of 8 to the first power, which essentially is just the cubed root of 8. Cubed root of 8 is 2 because 2 times 2 times 2 is equal to 8. And then we'll multiply and get negative 10. All right. In this example, we're going to try to come up with the function given a table of values. Okay, so remember that our function is going to be in the form of a times b to the x power. So we just need to be able to determine our a value, which remember is the initial value. It is also the y value when x is 0. So if you look at the table, these are the initial values right here. All right, so for f of x, the initial value is 3, and for g of x, the initial value is 5. So essentially, these are the a values, okay? All right, now, to find the base, you want to try to figure out the pattern in the y values, okay? So let's look at f of x for a minute. It starts with 3/4 and then goes to 3/2. And I know it may not jump out at you at that point, but essentially what's happening is you're multiplying by 2. Okay, so to go from 3/4 to 3/2, you're multiplying by 2. To go from 3/2 to 3, you're multiplying by 2. To go from 3 to 6, you're multiplying by 2. 6 to 12, you're multiplying by 2. So the base is 2. Okay, so f of x is going to equal 3, which is a, times 2 to the x power. All right, let's look at g of x. Again, let's try to figure out the pattern in our y values. We go from 20 to 10, from 10 to 5, from 5 to 5/2. So here, you're multiplying by 1/2. So g of x is going to be equal to 5, because that was our initial value, times 1/2 to the x power. Okay, now we're going to get into the graphs of exponential functions. So we're just going to start by graphing with a table of values, which I know is kind of a long way to do this, but just to get an idea of what the graphs look like. And we're going to graph f of x equals 2 to the x power, and g of x equals 1/2 to the x power. But let's start with f of x. So again, we're essentially just evaluating the function. We're going to start by finding f of -3, which means we're going to plug in -3 to our exponent. Remember, to get rid of a negative exponent, you flip it or find the reciprocal, and then 2/3 is 8. So this would equal 1/8. Okay, let's find f of -2. Again, we're plugging in -2 to the exponent. To get rid of the negative exponent, we'll flip it, and then 2 squared is 4. Okay, f of -1 becomes 2 to the -1st power. That becomes 1/2, or 1/2. All right, f of 0 is equal to 2 to the 0 power. And remember, anything to the 0 power is equal to 1. All right, then it becomes pretty easy. We're plugging in a 1, 2 to the 1st power is 2. Plugging in a 2, 2 squared is 4. Plugging in a 3, 2 cubed is 8. Okay, so let's plot those points. I'm going to start with 0, 1, and then 1, 2, 2, 4, and then 3, 8. All right, and then I know when my x values are negative, essentially my y values are just getting smaller and smaller, or approaching 0. All right, so this is the graph of f of x. Okay, let's do the same thing for g of x. So I'm going to make some room here. So we're going to plug in for g of x now. Okay, so we'll start by finding g of -3. So that'll be 1/2 to the -3 power. Well, to change that negative exponent to a positive, we just need to flip the base. It's already a fraction. So this will become 2 to the 3rd power, which is 8. Okay, g of -2 is 1/2 to the -2 power, which becomes 2 squared, which is 4. All right, g of negative 1 equals 1/2 to the negative 1, which just equals 2 to the first power, which is 2. All right, 1/2 to the 0 is 1. 1/2 to the first power is 1/2. All right, g of 2 is going to be 1/2 squared. So you just square your numerator and your denominator. And you've probably already noticed that our values are just flipping around. So if we plot these points, this graph also goes through 0, 1, and then we have negative 1, 2, negative 2, 4, and then negative 3, 8, and essentially it's going to look like this. All right, so the graph of the exponential function kind of depends on what the base looks like. So here we graphed 2 to the x power and 1/2 to the x power. Here's a picture of some more graphs with different bases, just so you kind of get an idea that it really depends on the base as to what the graph looks like. But I do want to point out that they do narrow down into 2 basic shapes. These are the 2 basic shapes of the graphs of exponential functions. And it really depends on the base. If the base is greater than 1, then the graph is going to be an exponential growth graph and look like the one on the left. If b is a fraction between 0 and 1, then the graph is going to be an exponential decay graph, or it'll look like the one on the right. Okay, let's run through some of the characteristics here. I do want to point out that these graphs have a horizontal asymptote, which is the x-axis. The domain is all real numbers. The range, though, is 0 to infinity, because you might notice that the graph is above the x-axis. It has an HA, which is y equals 0. And this particular graph is increasing. All right, our next one. A lot of the characteristics are the same, like the domain is still all real numbers. The range is 0 to infinity. It still has an HA, y equals 0, but this graph is decreasing. And I'm going to put from negative infinity to infinity, increasing from negative infinity to infinity. Sometimes we might say it's increasing or decreasing over its domain, and since the domain is all real numbers or negative infinity to infinity, that would suffice. But these are what you can consider your parent graphs, okay? These are the graphs, the basic shape you want to start with, and then we're just going to apply the transformations. Okay, so let's look at some examples of transforming these graphs, because we just want to be able to come up with a quick sketch and not have to go through a whole big table of values like we did. Okay. All right, so here we want to sketch the graph of f of x equals 2 to the x minus 3 power. Well, the parent function here is 2 to the x power. So we're just going to kind of draw that basic shape. The base is greater than 1, so we know it's exponential growth. And it has an HA at 0. Okay, then think about the transformations. Because the minus 3 is part of the exponent, you can think of that as being inside the function. So that's actually going to shift the graph right 3. So all we really have to do, and you can a lot of times use the 0.01 as a point to just shift right 3. And then we're just going to draw that same basic shape. And the HA would not change for this one. Okay? All right, let's look at another example. Here we have 2 to the x plus 1 minus 7. So again, the parent function is 2 to the x power, which is an exponential growth graph with an HA at 0. And then the transformations this time, the plus 1 is going to shift the graph left 1, and the minus 7 is going to shift the graph down 7. Okay, so if we shift the graph down 7, that's going to shift your HA. So the new HA is going to be at negative 7. So I'm going to sketch that first. Then what I'll do is I'll use this point 0, 1 as a point of reference, and then I'll just go left 1, down 7, and it should end up right above your HA. And then you're just drawing that same basic shape. Okay? All right, let's look at g of x, which equals 3 to the negative 2x power. So here, again, the parent function is 3 to the x power. So that's an exponential growth, maybe a little bit steeper, or it's going to grow at a faster rate than 2 to the x power. Okay, now the transformations. The negative 2, this is inside the exponent, okay? So the negative is going to reflect the graph over the y-axis. It's going to be a horizontal reflection. And then the 2 is going to be a horizontal compression, or shrink, if you want to use that word, by 1/2. Because you have to find the reciprocal. Okay, so we're going to flip it over the y-axis, so it's now going to be decreasing instead of increasing, and we're going to horizontally compress it by 1/2. So if you think of walls closing in on it horizontally, the graph is going to move closer to the y-axis. Okay, so we're just going to make it a little bit closer to the y-axis compared to our parent function. And because we're not shifting it up or down, it's not going to change the HA. Okay, let's look at this example. This time, our parent function is still 3 to the x power. But this time, the negative 2 represents the a value. Okay, so you might remember that that is also your y-intercept. So we do actually know that the y-intercept is negative 2. Actually, let me start with my parent graph, which would be exponential growth. Okay, for my transformed graph, since the a is negative 2, that is also my y-intercept. Okay. Essentially, for your transformations, because a is negative, it is a reflection over the x-axis, or a vertical reflection. And then because a is actually, the absolute value of a is equal to 2, that's a vertical stretch by 2 as well. So you guys, we're just using the same transformations that we learned in the very first chapter. If you feel like you've forgotten those, you might want to go back and rewatch that video. But okay, so to sketch this graph, we're not moving it up or down, so the HA is still going to be at 0. And we're just going to kind of vertically stretch it And remember, it was flipped over the x-axis. So it might look something like this. Okay, so I hope you kind of noticed as we were sketching those graphs the answers to these questions. Which transformation will change the domain of an exponential function? Well, the answer is actually none. Okay, the domain is always all real numbers. Which transformations will change the range of an exponential function? Well, remember for the parent graph, the range is 0 to infinity. Let's look back at some of our graphs. Here, because we reflected the graph over the x-axis, instead of the range being 0 to infinity, the range this time is negative infinity to 0. So anytime you reflect over the x-axis, that's also going to change the range. Here we did not change the range. It would still be 0 to infinity. Okay, here we did change the range. For the parent graph, it's 0 to infinity. But for the transformed graph, the range is negative 7 to infinity because we shifted the graph down 7. And if we go back here, we just shifted the graph right 3. That didn't change the range. It's still 0 to infinity. So the only transformations that affect the range of an exponential function are the vertical transformations. Okay? So more specifically, a reflection over the x-axis or a shift up or down. Okay, so you really have to kind of pay attention to those transformations when you're thinking about the range. Okay, in this example, we're going to be writing the exponential function given the graph. So all we really need is a point on the graph. We're going to start with y equals a times b to the x power. And we are going to plug in the value of x and y that we are given from the point. And we actually know, based on that y-intercept, that a is equal to 1 here. Okay? So we're just going to plug in everything that we know. A is 1. A point on the graph is 2, 9, so that gives us an x and a y value. And we're just going to solve it for b. So this will just end up being 9 equals b squared. Now, at this point, you're just going to solve it mentally and think, okay, what is the base? If we're squaring it and it's equaling 9, well, the base would have to be 3 because 3 squared is equal to 9. So essentially, we know that the function is y equals 3 to the x power. Okay, we need to talk about the number e. The number e is defined as the value that 1 plus 1 divided by n to the nth power approaches as n becomes large. When you get to calculus, you'll learn this as the concept of a limit. But if you notice, we've got a table of values here. For some values of n, where n is getting really big, because here n is 1,000,000. Okay? So as n gets really big, this value, if you notice, is getting closer and closer to approximately 2.718. And that is actually the value of e. Okay, E is just a number. It comes up a lot, which is why mathematicians gave it a symbol, okay, just like pi, which is 3.14. E is approximately 2.718. It is an irrational number, so we cannot find the exact value in decimal form because it's a decimal that never ends and never repeats. Again, similar to pi. Okay, now, often we will use what is called the natural exponential function, okay, which is just f of x equals e to the x power. Okay, that's called the natural exponential function. Well, because e is approximately 2.718, if you were to sketch its graph, it's going to be somewhere in between y equals 2 to the x power and y equals 3 to the x power, because e is between 2 and 3, a little bit closer to 3. So the red graph here represents y equals e to the x power. You may have noticed on your calculator that you actually do have the value e. Okay, so let's say we want to graph an exponential function with base e. We're essentially doing the same thing. Here the parent function is e to the x power. E is approximately 2.718. That's greater than 1, so again, it's going to be an exponential growth graph. And then we'll describe the transformation. So the negative in front is going to reflect the graph over the x-axis. The -3 on the inside is going to shift the graph right 3. And then the +4 is going to shift the graph up 4. Okay, so to sketch our graph, I would start with the HA. Since we're going up 4, the HA is going to now be at +4. And then just use the point 0.1 as a point of reference. We're going to go right 3, up 4. It's going to end up right here. Let me take that back. We need to reflect it first. Something wasn't working out. If you have a reflection, make sure you reflect the point first. Okay, so we're going to take the point 0.1. We're going to reflect it over the x-axis, so it's going to end up here. And essentially right now, your graph would look like this, if you were doing a dashed graph. Okay, so now we're just going to shift that graph right 3, up 4, and it's going to look like this. Okay? All right. We're going to stop there with the video, and we'll definitely, practice this some more in class. Thanks for watching. Have a good night.